like I said last time, we're trying to say a lot of psychophysics, how you judge, how you figure things out, how danger, how late, how something is based on your feeling. And to calibrate those feelings, we're going to use regressions. So I'm going to come back and show the regressions a little more and in the Powers law. Okay, so first thing first, I'm just going to run this. Okay, people, look at this. Okay, if I'm showing you, you see a face here, right? In the first picture, and gradually the face turn into Little Mermaid. Agree? Right? And then on the other hand, you can see that the Little Mermaid gradually turn into a face. Okay? And first thing first, let me ask you this. Which one you think that if you're coming up from here, okay, from this one, gradually looking down, when you start recognizing, there is a Little Mermaid there. Number 5, number 6, number 7. When did you start seeing the Little Mermaid? Oh, until you reach the second row. And then let me ask you the opposite way. Okay? If from Little Mermaid, let's just say that from the bottom, this one gradually moving up, when did you start feel like it's not Little Mermaid, I see a guy's face? Number 5, number 6, number 7. Well, so the argument I'm trying to have here is that if we consider there is a transfer function from something, from good situation to bad situation, there is a transfer function. Gradually move from yes, no, I don't see it, till yes, I see it, or the other way around. So psychophysics, in this case, we're really trying to see is that when is that transfer function happen, okay? And usually there are a couple different ways to do it. One is called method of constant stimuli. So we'll have usually 5 to 9, 7 plus minus 2, 7 different stimuli that repeatedly presented, and human subject is asked whether they perceive the stimulus, if either they see the Little Mermaid or not. And they should be equally spaced based on some algebraic definitions, but gradually along the intensity axis that can be selected so that the smallest value is almost never detected and the largest value is almost always detected, but somewhere in between you need to come up with a score, okay? And to do that, you just say yes, yes, no, I don't see it, and gradually, from, oh, I don't see it, until, yeah, I'm 100% sure I see it. You try to figure out where is that 50% line. And you find that 50% line, you find the constant stimuli. I'll come back to talk about the regression for this, but that is the purpose of we're doing this, because we're basically trying to figure out where is the VAR point. Oh, I can feel it around here, or I will say that, remember I said Colin Powell takes 75% risk or 80% risk, okay? And the points we're trying to come up with, okay, for the this whole thing is we're going to measure what we call constant error based on point of subjective PSE subjectively equal 50% to some stimulus we're trying to measure, and the differences we call it constant error. Okay, and also some people they just kind of they want to use confidence interval. So usually is figure out the 50% line, figure out the 75 and 25% line, and then use the differences from 75 minus 50 and 50 minus 25, and that range basically is from 20. See here, 80.6 is the 50%. 83.3 is 75%. 78 is 25%. So you cancel out the middle point. You try to figure out where is the difference threshold by using the 75 minus the 25 divided by 2. Okay, and to do this, okay, we're really trying to abuse two different functions. One is the logistic function. The other one is what we call the normal distribution. And the normal distribution back here, in normal distribution, the nickname in psychophysics is called probit. In logistic regression approach, it's called logit. But no matter logit or probit, it's really end up in a regression format. Okay? So let's show the logistic regression, and I'm going to do this first. Go through the same Excel file, so you will feel like this is boring. Going to do it again, but sooner or later, when you combine everything together, it will make, you just see that it's all regression. So see here, first, the stimulus is equal space for how many times? About 9 times, right? Usually we can highlight the middle point, okay? 7 plus minus 2, so here we'll have 9 different stimulus. Are they equally spaced? 4, 6, 10, jump by 2, right? So they're equally spaced. And then when I first start saying that I give you 100 times, only 4 times you can hear it, or very, very low level. Here you said that, 7% of the time people say, yeah, I can hear it. But 20% of the time, you see how high it is, you're going to end up 98% of the time. So first things first, if you plot this curve between okay, let me do it. Okay, so this is not a perfect curve, right? But we're trying to move from absolutely nothing to 100% something. Can you see that there's almost a transfer function going on? Can you see that? 0 to 1. Okay, so we're basically trying to say that, okay, how to linearize this. The way how we linearize this is through z-score. So the z-score equal to normal S inverse. That will give you the z-score. Can you see that? Normal inverse. And so if you plot, okay, the stimulus against the z-score, you will see almost correlated like a straight line. So our job is trying to say that how does the stimulus and z-score correlated into a straight line, and what is the intercept and what is the slope. So if you do that, you'll see that I can do it again. Okay, slope is based on z-score. Intercept is based on z-score. Okay? And what's your constant stimuli is your 50% point equal to your intercept divided by your slope. That's where you cross the 50% line. And you call that as your constant stimuli. Okay, that's your 50% line. Okay, so roughly you can see it here, right? Okay, intercept. Scare me for a sec. Okay, yeah. Y value is your Z value, and X value is your stimulus. So far, so good? Yep. Okay, so we just abused regression, but that's not the point. The point is, what does it mean? Okay. Okay, and what does it mean? Back to the simple regression. And I'm going to do this one more time because Weber's law, we have the simple regression problems there too. So y is equal to intercept b times a times the physics. So far, so good? Z-score is intercept plus the slope times the physics, the stimulus. Is that okay? That is our model. And so you can think about it this way, okay? I know that this is a summation of the sum of square, the error term, equal to the differences between the two. But usually this is how I remember the whole things, okay? First, I have a bunch of z, so a bunch of z. And then b term, I have how many b? I have n observation, 9 observations, so mb. And then I have my a term need to be estimated through a bunch of physics. So far, so good? So see here, summation, basically a bunch of this, a bunch of this, a bunch of this. A bunch of z, a bunch of b, 9b, 9 observation, and then a times summation a bunch of x, or the physics. Next, the interactive part. So everything times phi. So z times phi becomes summation z phi, and b term summation phi, because now I have b term a bunch of phi. And then phi again, phi double becomes summation phi score. So this linear regression, if you use sum of square error term, you will end up with two simultaneous equations. What do you know? You know summation z. You know b, you know n. You know summation phi. You know summation z times phi. You know summation phi. You know summation phi square. The term you need to estimate or figure out is where is my a term, where is my b term. So you become two simultaneous equations. A term and b term, they have the same determinant. The determinant in the denominator, which is n summation phi, summation phi, summation phi square. N summation phi, summation phi, summation phi square. And then on the top, you copy the same denominator except the part you're interested in. If you're interested in b part, you put a summation phi, z summation z phi here on this determinant. So now this will give you the b estimate. And then for the the A part, summation, this two terms replaced by summation Z phi, now get this part. So now you can do this regressions manually one more time. Okay, I'm going to do this one more time. This time, I'm going to have this one now. Okay, so what do I need? First, n, I need to know. N equal to count. How many? One do I have? 9. And then I need summation phi. So summation phi symbol. Okay. Okay. I don't know why this is locked. Okay, here we go. So summation phi equal to sum of my stimulus. Okay? And then I need to have summation phi square. So I need to have this guy square for my cell superscript. Okay, so that should equal to sum square of my physical stimulus. And then I need to have summation Z phi. Okay, so or Z phi or phi Z, that's fine. Oh, let me do it this way. Okay, so I need to have a summation Z phi, sum product of phi and Z. Okay. Oh, sum product. Okay, and now I have Z phi, and then finally I need a summation Z. So I need a summation Z. So what is the denominator? Denominator is basically equal to n times summation Z phi square minus summation phi, summation phi square. Okay, that's my denominator. Okay. And then my A term should equal to, what's my A term? Let me do my B term first. I have B first. My B term equal to summation Z. Oh, I didn't do summation Z yet. Sum. Okay. So B term equal to summation Z times summation phi square minus summation phi times summation phi z, or z phi, and this whole things need to be scaled by the denominator, which is this guy, okay? And you see the intercept calculated exactly the same way. Well, I have different, no, I'll, the B? Phi is what? Is your physical arrangement, right? Yeah. Okay, so far so good. And let's do our A term. And A term, you know, this is not different from our design experiments regression, X transpose X, X transpose Y. A term equal to N A term equal to A term N times summation Z phi minus summation phi times summation Z. Okay? And this whole thing's divided by your denominator. Okay? And if you make this guy's spread out, spread it out, that's the same thing. And what is your constant stimuli? CS. Your CS is equal to your intercept I need to put a negative sign out. If I don't, you're having the wrong side. Okay, divided by this guy. Okay, so it's relatively about constant stimuli is somewhere around 12.
I was following along, and I seem to have a different number for phi squared.
Summation phi square.
Yeah.
Why? Okay, let's do it again. Okay, phi is the physical stimuli, and then we're having a constant step by 2. Okay, and we can do it differently.
Why did you do, in that cell, obviously the math works out, but why did you do
Sum square.
sum square and not just sum?
Oh, because it's phi square. Summation phi square. Look at the equation. Here's phi square, right? Phi square is the physical square. Here, I'll do it differently. I'll do it here, equal to this guy's times itself. And if I sum it, you got it? Mm-hmm. Okay. So now I'm basically showing you that we're doing linear regression. We know that in DOE, I said that, let's try to minimize the sum of square between your observation and your predicting value. And then your partial derivative for A, partial derivative for B, you'll end up with this simultaneous equation, and then we solve the simultaneous equation. But look at these two equations, denominator and numerator, what is really involved? Denominator, since it's equal space, you can consider this denominator really is what? Is the variance in disguise. Would you agree with me? N times phi squared minus phi, summation phi times summation phi, right? So denominator really is about how this stimulus spread over a range. Okay, so within this range, okay, I would like to know how high can you go, because if I know how high can you go divided by this range, that's arctangent, that's your slope. So now we try to figure out what is your slope. Is, okay, here, a term, the denominator, got two different way of doing things. We're saying that it really can be considered, I think I did it last time a little bit, is basically saying that, here, I have a bunch of format shape, no fill. Okay, so people, I know that I have one observation. If I only have one observation, what is the slope? The slope is from how high you are divided by how, and your base, right? That's your slope. So now, so it really is a bunch of z and phi. I jump, I jump, I jump. So now I'm saying that, okay, you jump many, many times, you jump many, many times. So I have a bunch of n times z phi. Okay, so z and phi is almost like that rectangle square. Agree? And that rectangle area, okay? A bunch of z, a bunch of phi, a bunch of z, a bunch of phi. So now if I have, okay, one small area, and I said, oh, grow a little bit, and then grow a little bit more, okay? If every time it's proportional, z grows this much, phi grows this much, z grows this much, phi grows this much. So every z times phi, or I combine all the z times phi together, they should be what? Kind of like a step. Boom, 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 increasing, increasing, increasing the same way. So you can consider that the denominator here is almost like how they co-vary over the variations of the stimulus. So co-vary over the variation, that is your slope. And let me do something, I did it in other class before, okay? And I basically try to show students this, okay? Say, I have a bunch of random number, okay? And I basically said that everything I have is equal to intercepts 3 plus 2 times my slope. And let me Control C, Control V, and let me lock the value. Okay, Control C, paste special, value, locked. Okay, and if this is the case, okay, and I can sort it, data sort, based on column E, and okay. So if I plot these things, it should be a perfect straight line, okay? And yeah, should be a perfect straight line, okay? And so if you have a perfect straight line, and I can say the correlation coefficient between these two gonna be 1. And then the next things I can say is that the slope, okay, is equal to this guy times the variance of this guy. Slope, oh, I haven't, no, I gotta, hold on. Let me do it this way. Slope first. Okay, so I got my slope 2. Okay, and then my correlation coefficients, let me get my variance. Oh boy, what did I do? Okay, some things. And update SAS microbes. Let's do it differently first. Okay, z-score and phi. Okay, so let me do it first. By saying that this is equal to 2 plus 3 times phi. So let me build a perfect system first. Pay special value. Okay? And let me show you what I did. I'm just saying that I have a perfect straight line. Agree? But now what I'm really interested in is that, oh, let me sort it, data sort. I hope it won't happen again since I avoid the, okay. Doesn't matter. All I care about is this. Everybody agree with me? Correlation coefficients is equal to 1 because it's a perfect straight line, right? And of course, if you do it the opposite way, is now I'm trying to calibrate this. all I care about is this, okay? If this is really z-score against the human at different stimulus, would you say this is a pretty sharp human calibrate this whole thing like a straight line? Stimulus increase a little bit, judgment change a little bit. Agree? Okay, and all I need you to do is this, okay? Can you find a number? Okay? I'm just adding a number. I can ruin this whole thing. Okay? For example, that's why I did the sorting. Is this, okay? If I copy this whole thing, okay? And then this is 0.05 here. The measurement should be 2, right? The z-score should be 2. If I don't use 2 as my z-score, I use somewhere around 4. Okay? I'm just changing one number. I just change this number, say it's 4. The correlation coefficients drop significantly. Why? Because I have one number here, 0 point something, and the measurement, I can have it even higher, 4.76. Okay? So this number is right here. Okay? What I'm saying is that if I have one measurement here, that will ruin the correlation coefficients. If I want to ruin the correlation coefficients even more, where should I add another number? Right here. Because that will make, remember I said a bunch of rectangle, increasing. Here, originally it's rectangle increasing. But now I'm saying that, hey, suddenly you have a rectangle coming up. See here? Small increment, small z-score. Small increment, small z-score. But if you have a value, boom, jump like this, that's wrong, right? So similarly, if I have another number here, at a point A something, I make it really, really small, 0.2, and I have the number as 2.1. Okay? See the correlation? Drop below 45%. So look at this whole thing. It's a nice line. All you need to ruin is the beginning and the end. Okay? Now let me play the game in the opposite. Well, let me do this in the opposite way. Okay? And in DOE, I let people play with this many times. Suppose, okay, I have a bunch of z and phi. Okay? And then let me just use random number. And here I'm just using random number to the 4, so times 4. Let's say times 5. Okay, so there's no relationship, right? There's no calibration involved, just a bunch of random number times random number. So if you look at the scatter plot, okay? No, hold on. Control C, on, pay special, value. Okay? If you look at the plot right now, insert, it's everywhere, right? So what do you think the correlation coefficient is going to be? Yeah, so we can do this. Control C, Control V. It's not big, right? But I would like you to also do the same things. Try to enforce the calibrations. So what you do is you will have one value here. When you're 0, you make it extremely small. Okay? 0, let me say that my z-score, I'll make it 0.001. Okay? And look at the correlation coefficient, improve quite a bit already. And then on the other hand, when you, oh, I should sort this. Give me a sec. Data sort. Okay, so let me just make this. If you calculate a correlation coefficient, originally it's 0.3. Nothing important. Okay, so now if I can make this guys extremely small, okay, 0.001, and make this guys extremely big, okay, 10, okay, and if you look at the correlation coefficient can improve quite a bit. So what I'm trying to show here is that whenever we do psychophysical calibration, the 2N, they are the most critical N. If you don't be very, very careful, and we say, oh, we calibrate the human very well. The 2N, the very, very small value and the very, very big value, you change it a little bit, you can change the correlation coefficient quite a bit. Okay, since I was late today because of the review, I'm going to let you go early. Okay? Thank you.